Everything around us, the salt we eat, the water we drink, even the air we breathe, is held together by invisible forces called chemical bonds. Without them, life would not exist. Let's explore how atoms connect through ionic and covalent bonds. This image explains the concept of an ionic bond using sodium, Na, and chlorine, Cl, as an example. At the center of each atom is the nucleus, which contains protons and neutrons. But for bonding, what really matters are the electrons shown as small dots on circular paths called shells, or energy levels. Sodium has an atomic number of 11, which means it has 11 protons in its nucleus, and in a neutral state, also 11 electrons around it. These electrons are arranged in shells, 2 in the first shell, 8 in the second, and just 1 in the third shell. Chlorine, on the other hand, has an atomic H number of 17, so it has 17 protons and 17 electrons in its neutral form. Its electrons are arranged as 2 in the first shell, 8 in the second shell, and 7 in the outermost third shell. The outermost electrons of an atom are called valence electrons, and they play the key role in determining how atoms react with each other. Now, the rule that drives this reaction is called the octet rule, which states that atoms tend to achieve stability by having 8 electrons in their outermost shell, just like the noble gases. Sodium, with only 1 electron in its outer shell, is unstable and can become more stable if it loses that 1 electron, leaving behind a completely filled second shell containing 8 electrons. On the other hand, chlorine, with 7 electrons in its outer shell, needs just 1 more electron to complete its octet. Instead of gaining 7 electrons or sodium losing 7, which would take too much energy, the simplest and most efficient solution is for sodium to donate its 1 electron to chlorine. That is why in the image we see an arrow drawn from the single electron of sodium's outer shell pointing towards chlorine's outer shell, showing the electron transfer process. Once this transfer happens, sodium no longer has that outer electron. It now has more protons, 11, than electrons, 10, giving it an overall positive charge, so it becomes a cation written as Na+. Chlorine, which has gained that extra electron, now has more electrons, 18, than protons, 17, giving it an overall negative charge, so it becomes an anion written as Cl. These two oppositely charged ions are strongly attracted to each other due to electrostatic force, which is simply the natural pull between positive and negative charges. This strong force of attraction is what we call an ionic bond. It is important to understand that ionic bonding is not about sharing electrons, as in covalent bonding, but about complete transfer of electrons from one atom to another. In the case of sodium chloride, this bonding does not produce just a single Na+ and Cl pair. Instead, in a solid crystal, millions of Na+ and Cl ions arrange themselves in a repeating three-dimensional lattice structure, where each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. This lattice maximizes attraction and minimizes repulsion, making the structure extremely stable. That is why common table salt NaCl forms solid cubic crystals. The ionic bonding shown in this image also explains many properties of ionic compounds. Because the ions are held together by very strong electrostatic forces, a lot of energy is required to break them apart, which is why compounds like sodium chloride have very high melting and boiling points. Ionic compounds are also brittle, because when stress forces like charges to align next to each other, strong repulsion occurs, causing the crystal to shatter. Another important property is that ionic compounds can conduct electricity, but only when they are molten or dissolved in water, because in the solid state the ions are fixed in place and cannot move, whereas in solution or molten form, the ions are free to move and carry electric current. Finally, ionic compounds are usually soluble in polar solvents, like water, because water molecules can separate and surround the ions, stabilizing them in solution. So, in summary, this image captures every stage of ionic bonding: the initial electron, configurations of sodium and chlorine, the transfer of sodium's single valence electron to chlorine, the formation of Na+ and Kel ions, and the powerful electrostatic attraction that holds them together. It demonstrates how atoms achieve stability through the octet rule, why electron transfer is favored, and how the resulting ionic bond gives rise to the characteristic properties of ionic compounds such as high melting points, brittleness, solubility, and electrical conductivity. In simple words, this picture is showing the basic chemistry behind common table salt. The reason why sodium, a reactive metal, and chlorine, a poisonous gas, combine to form a stable, safe, and essential compound that we use in our daily lives. In the previous image, we saw that in an ionic bond, electrons are completely transferred from one atom to another, creating oppositely charged ions that are held together by strong electrostatic attraction. However, this is not the only way atoms can bond. When two nonmetal atoms, or sometimes a nonmetal and a metalloid, come together, they usually cannot transfer electrons as easily as metals and nonmetals do. Instead, they achieve stability by sharing electrons, which leads to the formation of a covalent bond as shown in this image. Here, atom A and atom B each have unpaired valence electrons in their outermost shells. Since both atoms need more electrons to complete their octet, neither is willing to give up its electrons completely. Instead, they overlap their orbitals and share pairs of electrons so that each atom can count the shared electrons toward its octet. The image shows that atom A, a nonmetal, and atom B, which can be either a nonmetal or a metalloid, each contribute one or more electrons to the shared pair. These electrons are not transferred but instead belong simultaneously to both atoms. As a result, the two atoms are linked together, forming a covalent molecule. For example, in a hydrogen molecule, H2, each hydrogen atom has only one electron, but needs two to be stable. By sharing their electrons, both hydrogens feel as though they have two, and the pair becomes bound by a covalent bond. Similarly, in a water molecule, H2O, oxygen shares electrons with two hydrogen atoms so that all atoms satisfy their outer shell requirements. Unlike ionic compounds, which form large crystalline lattices, covalent bonds usually result in discrete molecules, individual units with specific shapes. The shapes of these molecules can be explained by the VSEPR theory, valence shell electron pair repulsion, which predicts that electron pairs arrange themselves as far apart as possible to minimize repulsion. This explains why water has a bent shape and carbon dioxide is linear. Covalent bonds can also vary in strength depending on how many electron pairs are shared. When one pair is shared, it forms a single covalent bond, like in H2 or HCl. When two pairs are shared, it becomes a double bond, like in O2 or CO2, and when three pairs are shared, it forms a triple bond, like in N2. The more pairs shared, the stronger and shorter the bond becomes. Covalent bonding is also responsible for many of the substances we encounter daily, including water, oxygen, carbon dioxide, methane, glucose, and proteins. Another important difference from ionic compounds is that covalent compounds usually have lower melting and boiling points because their molecules are held together by weaker intermolecular forces rather than the strong ionic lattice. They are often gases, liquids, or soft solids at room temperature. Most covalent compounds also do not conduct electricity because they do not contain free ions or charged particles, although exceptions exist, like graphite. So, this image shows how two atoms with unpaired valence electrons achieve stability, not by transferring electrons, but by sharing them, resulting in a covalent bond. Together with the earlier ionic bond image, we now see the two major ways in which atoms combine to form compounds: ionic bonding through electron transfer and covalent bonding through electron sharing. Both follow the octet rule, but they achieve it in different ways, which is why ionic compounds like sodium chloride are very different in properties from covalent compounds like water or carbon dioxide.